Good morning everybody. Today we will be starting with the first practical, that is the determination of dissolved oxygen from water samples. So what is the importance of dissolved oxygen? Why we need to study about the dissolved oxygen? So dissolved oxygen is a very essential component in the water system because it supports a lot of life forms in the water ecosystem. So the depletion of this dissolved oxygen will greatly affect the ecosystem in the water bodies. So what are the different reasons which reduces the dissolved oxygen? So the reasons may be the anthropogenic activity, that is the rapid industrialization has brought about a lot of people from the different places, and then these households have increased the effluent from the different systems, and then the industrial effluents are also reasons for the entry of these effluents into the water bodies. So what will happen here if you don't check the dissolved oxygen levels? The dissolved oxygen levels will greatly reduce in the water system, and then the water ecosystem will be greatly damaged. So here the principle of this particular dissolved oxygen goes like this. So here you have different components which we use for the estimation of this dissolved oxygen. One of them is the manganese sulfate solution and the alkali azide solution. Here in this case, what will happen is, once the water sample is collected, the water sample is added with the manganese sulfate solution, and this manganese sulfate solution will give out the potassium hydroxide and the manganese hydroxide, which is a white precipitate, and K2SO4. This particular manganese hydroxide with oxygen will form manganese oxyhydroxide, and this manganese oxyhydroxide in presence of this oxygen in presence of H2SO4 gives out the iodine or potassium iodide, and this potassium iodide which is a brown color precipitate will give out iodine, which is one of the ways wherein we will measure the oxygen indirectly with the estimation of this particular iodine, which is this whole experiment is iodometric titration where we carry out this particular experiment. So these are some of the requirements. Basically we need a water sample, the sodium sulfate, which is used as the titrant, and manganese sulfate is added to the water sample around 2 ml, and then the same amount of alkali azide solution is added, and then starch is added as an indicator, and the concentrated sulfuric acid is added to dissolve the precipitate that is formed, and then for the calculation purpose, dissolved oxygen is always expressed in mg per liter. Mg per liter. So this is the formula that we will be using for the calculation of the dissolved oxygen. So this is the table which we need to know for the titration to be or to begin the titration. Let us now try to know how the water sample is collected. So the whole BOD bottle has to be submerged in the water, and you have to ensure that there are no air bubbles, and then the stopper has to be placed in the water itself to see that there are no external air bubbles within that, and there will be water near the stopper which is permitted. That's it. So this is the way how water has to be collected. The BOD bottle has to be immersed in the water because we are doing it with the tap water. I am showing it you in the tub, but when you are collecting the water sample from the water bodies, this BOD bottles has to be completely immersed, and you make sure that you stopper the water bottles within the water itself to ensure that the external oxygen doesn't enter into the bottle. The first reagent what we are going to add now is the manganese sulfate solution, which we have to add now. 2 ml of the same solution is added into the BOD bottle. The pipette has to be introduced into the water and you release the solution into the water. Once you ensure that the whole of the solution has gone in, you can take out the pipette and immediately stopper it back. So the excess water has to be put out. The second reagent what we are going to add now is the alkali azide solution. So this has to be always taken with the rubber teats or with this pipette sucker, so that you never pipette this alkali azide solution. So 2 ml of the same solution is taken and then it is introduced into the you see the cloudiness that is formed in the water. Stopper it and you allow this precipitate to settle down in dark, or it can be kept as it is, and see that the precipitate settles down to half of the BOD bottle, and then the next acidification procedure can be carried out. The BOD bottle, once the 2 reagents are added, it has to be gently mixed to see that the 2 solutions what we have added is mixed, and then it has to be kept in dark or at the same place for 20 minutes for the precipitate to settle down. See, you can observe the precipitate has settled down. It is the end of 20 minutes, and then we are now adding H2SO4 to acidify the precipitate. With the addition of the H2SO4, you can see that there is a change in color of the precipitate. The white color precipitate has now turned reddish brown, indicating the release of iodine in the water sample. The BOD bottle is now closed, and you need to mix the BOD bottle, because the addition of H2SO4 should dissolve the precipitate that is formed. And ensure that the water becomes clear, or the whole precipitate is dissolved. If the precipitate is not completely dissolved, you can add a little more of the acid to ensure the complete dissolution of the precipitate. Now the water sample after adding concentrated H2SO4 has attained a clear solution. So this can go in for the titration. So for the titration we will be using the sodium thiosulfate as the titrant, and you can see the normality of the sodium thiosulfate here, and this has to be added to the burette, and here the burette is filled with the ensure that the burette is completely and neatly filled, and see that the end point is initial 50 ml of the sample is taken from the BOD bottle, and then it is added to the conical flask. Then add 1 ml of starch, because starch you don't have any problem, you can mouth pipette it. The solution has become blue. Now we'll titrate it against sodium thiosulfate. The end point is blue to colorless. Once again, ensure that the initial burette reading is 0. So you have to add the titrant slowly, because dropwise, and see that it has become colorless. And then check for the burette reading. And the burette reading reads 0.4. Replace the burette into the burette stand and go for concordant readings. So the next titration has to, so 50 ml of the sample is taken for the second reading, and to that you will be adding 1 ml of starch. As I told you, because you don't have any problem in pipetting starch, you can take it. Now the end point is blue to colorless. You have to carefully do this, because your readings will come in points. So 1 or 2 drops, a maximum of 3 to 4 drops, you will get the reading. See, you have got a clear solution. So you have carried out the titration till you get concordant readings, and this can be used to calculate the dissolved oxygen. See, after the titration, as you have seen, we have performed the titration, and then the burette readings are recorded here on the board. The initial burette reading was 0, and the final burette reading was 0.4, and then the volume rundown was 0.4. And then for the concordant readings, we went for the second trial, and then we got 0.9 as the final burette reading when the initial burette reading was 4, and then the volume rundown was 5. The final burette reading was 1.3, and the initial burette reading was 0.9, and then the volume rundown was 0.4. So the average of these mean of this came to 0.4, and this was taken for the further calculation of the dissolved oxygen. So the calculation goes like this. That is, for the calculation of the dissolved oxygen, you need a formula wherein the dissolved oxygen 8 is a constant, and because the dissolved oxygen is always calculated for 1 liter, that is, it is expressed as grams per liter, milligrams per liter, 1000 we take, and then this is the normality of the titrant, that is the sodium thiosulfate what we have taken, and this is the burette reading that we have got. And this is the volume of the sample that we have taken. That is, initially for the titration we have taken 50 ml of the sample. So this is the volume of the sample. So here in this case, our normality of the sodium thiosulfate is 0.025 and the burette reading is 0.4. When you multiply or substitute it with the formula, we get 1.6 as mg per liter as the dissolved oxygen for the particular sample that we have taken. And here in this case, this is this one for tap water in this particular case. Today we will be discussing about the biological oxygen demand. The very purpose of the determination of the biological oxygen demand is to know the amount of the oxygen that is there in a particular water sample. So here this biological oxygen demand stands for the amount of oxygen that is there in a particular water body. As the microorganisms increase, the dissolved oxygen levels will get reduced. So as you have already know that how the dissolved oxygen level has to be calculated or performed, the same procedure is followed for the determination of the biological oxygen demand. Initially, when you are collecting the water for the estimation or the determination of biological oxygen demand, we need to collect it in a second bottle. The two bottles has to be brought into the laboratory, and one dissolved oxygen bottle what has the water sample that will go into the BOD incubator, which will be incubated at 28 degrees centigrade in tropical and subtropical countries. In colder climates, it is incubated at different temperatures. So the dissolved oxygen for the first sample is carried out, and you get to know the dissolved oxygen levels on the day 1. So for the estimation of the BOD, the sample which is incubated in the BOD incubator is taken at day 3, and then the same protocol is followed for the estimation of the BOD by taking the BOD bottle and then adding 2 ml of the manganese sulfate solution, followed by 2 ml of the alkali azide solution, and then the precipitate is formed, and that precipitate is dissolved by using concentrated H2SO4, and then that is digested, and then that sample is taken for the estimation. So generally what happens is when we start estimating the dissolved oxygen levels after incubation, it is seen to be less. The reason being the microorganisms which are there in that water sample, they try to degrade the organic matter that is there, and they use it, and this is an aerobic process that is taking place. So when such sort of a reaction takes place, the dissolved oxygen levels tend to drop down after the day 3. So here in this case, the beauty of the sample, which is expressed in mg per liter, that is you take the BOD, and then where D1 is the initial DO on the day 1, and then D3 is the dissolved oxygen after incubation for 3 days, which is again expressed as mg per liter, and therefore BOD equals D1 minus D3, that is on the day 1 we had got the dissolved oxygen as 1.6. On day 3 the dissolved oxygen level has dropped down, and finally the dissolved oxygen level or the BOD level is come down, that is 0.8 mg per liter. So when we talk about the BOD, we are talking about the same procedure wherein we have carried out for the dissolved oxygen levels. The BOD is calculated as the D1 minus D3, that is D1 is the first day reading and then the D3 is the second day reading. So finally the BOD of the given sample, that is the tap water, is 0.8 mg per liter. So if the same water samples are taken from the different sources like lakes or any other water bodies, the BOD levels and the dissolved oxygen levels will vary, or it will be on a higher scale when compared with the tap water. So this is how the dissolved oxygen and BOD estimations are carried out. Thank you.